Okay, I think we're recording. Share screen, and let me make sure that indeed we're using the microphone that is correct. Yes. Very well. So welcome, Don Frederi.
Hola, don Pablo.
Hola, Don Frederi. Tío Frederi.
Tío
So,
Pablo.
so we're both tíos.
Yeah.
Care to say where we are and what we're about to do?
We're in Michigan and outdoors, and we are about to chat about Bayesian statistics.
Fantastic. We're in your farm because you're a
Right.
farmer beyond a statistician, a Bayesian statistician.
Yeah, this is a farm. I'm just a farmhand.
Yeah. Very well, fantastic. I hope that everybody on the other side are joining us, and I don't know how many times we're going to use this, but hopes that wherever you are, you're having a blast with our video. Let me try to see if I can move our heads. Maybe we're going to put this on the corner. We're saying hi to the second camera. Okay, perfect. So yeah, we're going to talk about Bayesian statistics. The idea is to give an overview before a series of presentations and talks for the math collaboration, but basically anybody that wants to learn a bit more about this can use it for useful things. Okay, so let's get started. We are going to aim to try to take half an hour for the whole thing. We'll see when the video ends how successful we were. The first thing that we're going to do is go talk a bit on why you will want to learn these things. What can you learn from data? We'll go through the Bayesian formulations and formulation and Bayes theorem. We'll discuss a typical day on a Bayesian statistician that is helping, in this case, physicists. And then we're going to go through some thoughts that I created that I think could illustrate some of the aspects in a practical way. And we're going to close with some remarks and a challenging problem for all of you. So the first part that we want to show is examples of what you can learn from data. So in here I have a bunch of plots. We can, of course, please interrupt me. This is not a monologue, but a dialogue.
Dialogue.
A dialogue. that is a joke from doesn't matter. Anyways, so the example.
I don't know bio. All I know is grass and heavy ions.
Very well.
Yeah.
And heavy sheeps. So the example.
Did you know that the plural of sheep is sheep?
No, I didn't know that.
Yeah, now you know.
And now the people at their houses know. So the examples that I put in here, some are directly from physics and science, like the discovery of the Higgs boson. And the idea is to convey that there is information that you will be able to observe when you basically observe phenomena in great numbers that a single event will not tell you, but the group of things will tell you. So the two examples from our actual field that I put is the discovery of the Higgs boson and this plot that I love that is trying to quantify what are the limits of the nuclear existence, and that comes after you're able to take into account many models, take the uncertainties of the models, and mix their prediction in a way that makes sense. This is our plot. Have you seen this plot before for COVID?
For COVID?
For COVID predictions.
That plot. No, the plot at the bottom I recognize because I think I'm a co-author on the paper that's listed there.
Yep. But the one on the top is made by a lot of people, including Oscar, and they were trying to make a test system and an alarm test system for predicting what is going to be the surge of new COVID cases.
Yeah.
This was while we were in pandemic. And it's a type of things that you can unlock once you know how to do Bayesian statistics. Do you know, Frederi, that smoke and lung cancer are correlated?
Quite a bit.
Quite a bit, right?
Yeah, I mean, you know, my grandfather died when he was 90, and he smoked his whole life and never got cancer. So yeah,
he's one of the outliers.
He's one of the folks who help us figure out the tails of that distribution that relates those two variables. Tails, they could be, you know, heavy tails, and we'll talk about that in a minute. I think when we start talking about priors. Yep. There's exactly. A thing called priors. We're going to find out what in the world that is.
And
priors.
That's the thing. I don't know how much we're going to use that video, but that's okay. So I was reading about it, and apparently there were like 6 studies that came in the 1950s linking these two things together. And before that, we didn't know. And when you start looking at the numbers, it's like, oh, this is obvious. There is a problem. These two things are correlated, and then eventually, once you find a correlation between two things, It's up to you to come up with a model on, can you explain if they're coming from the same cause, because correlation doesn't imply causation, and to try to see if that model makes sense. And for that example, I have this other correlation here on the left corner that a friend of mine, a professor at Michigan State, told me that he found out this. You know that there is a strong correlation between grandparent mortality and whenever a test comes for undergrad students?
Because
Yeah,
it maybe happen around the same time of year.
no, yeah, that whenever you're giving a test, a bunch of students are reporting that their grandparents died and they cannot attend the test, and
You
they
mean
have to go.
reports of grandparent mortality?
Reports of grandparent
Reports
mortality.
of grandparent.
So that's very
Got it.
important.
Yeah.
So that is taking into account the source of your data, and then trying to understand if there is a model that could explain that indeed, whenever your grandkid is taking a test, you are at risk of suffering a problem. Those are the dogs
We would
that
like
are.
to know whether there really is a real connection between grandparent mortality and student testing, but there is a connection with reports.
Yeah, exactly. And the final example that I put in here, so this is kind of like a counter example in that sense, that we need to be careful on how we treat our data. The final example that I put in here is the German tank problem. And I just find it fascinating. It's a very interesting question. Is that suppose that you observe, in this case I made up the numbers, but you observe 5 tanks with some numbers, 7, 52, blah, blah, blah.
Those are labels on the side of the tank, like you have in that picture.
Exactly. So the idea is, can you estimate the number of tanks that the enemy has? And if you imagine that if you see these numbers, the likelihood that actually there are 3,000 tanks out there, and you just happen by chance to see only numbers between 0 and 100, is very slim. So you can actually use statistics to estimate that number.
Yeah, it relies on certain assumptions about what we're looking at, such as, all these tanks have different numbers and things like that. So, there's probably more that we need to know before we answer that question. And one of the things that we would have to do is to make sure that we understand what we mean by a label for a tank, whether we really do assume that every tank has a different label, and things like, what our prior information is on what the chances are that the tanks that we observed were part of a specific phase in the war, and things like that. So it could be very complicated depending on the information that we have. And then folks might even start arguing with each other about what prior information we should be using. So yeah, and we can always simplify these things by just making simple assumptions. But yeah, so let's talk about that.
Very well.
As we move forward.
So this was a motivation in a general sense. You want to mention something?
Yeah, there was another example which is not on these slides, and I forget who it was. It was a British mathematician who was working during the Second World War, trying to figure out where they should put armor on the airplanes, and the military intelligence was looking at the airplanes that were coming back to base after having been shot by the Luftwaffe. And they said, well, look at all these places where these planes are getting shot. We should put armor there. And then the mathematician said, no, maybe not. Maybe we should actually put the armor in the places where there were no bullet holes, because the planes that had bullet holes in those places didn't come back to base. And indeed, that's what they did. They decided to armor the nose of the plane, because not a single plane that was shot in the nose or on the engines came back to base. And so then, based on that, intelligent way of interpreting missing information in the data, they were able to, come up with a much better way to armor the planes. So there's always, you have to look at the data that you have, see what it means, ask yourself, do I have all the data? What might be missing? And if I have something that's missing, can I impute it from some other proxy which is in front of me? Things like that. So all those things are important.
That explanation on the planes is on the survivor bias article in Wikipedia. And it has a nice picture. And it's a fantastic read. And I agree. It's shifting your view is like, oh, this data is telling me exactly the opposite, that I need to put armor on the locations where there are no holes. So perfect. Thank you, Frederi. So in here, we're going to go through the Bayes formulation, Bayes theorem, and on a very specific example related to nuclear scattering. It can be any experiment in nuclear physics. It can be anything not in nuclear physics, but we want to use this one because most of the time we're playing with nuclear physics friends. So imagine that you have some experimental data that we put here in the blue points with some error bars, and you're trying to feed a model F. That depends on some parameters. It could be the radius of your nucleus, the diffuseness, how strong the nucleus attract particles, etc. And what you want at the end is to be able to fit your model and report some uncertainties on your theoretical predictions. And we like to do that through Bayesian statistics. And we're going to talk about this term in a second, but this is how I see things. And please complement or disagree if you see it differently. The philosophy that I see in Bayesian statistics is that everything is a random variable. You might choose not to believe that, and you might choose to say, this particular thing I'm going to assume it as known, and that's okay. That is part of your formulation, but in principle, everything that you're dealing with should be treated as a random variable. And the challenge is that you need to model the distribution of the random variables and how they interact with each other. And that is one of the things that is called uncertainty propagation.
So let's go through this notation to make sure people know what these letters represent. So you have alpha, so that's a set of numbers. Is it like you said it was parameters? That was one or two numbers that are used inside the model. The little f is the model, right?
The little f is the model, yeah.
Little x and little y, what are those things? I mean, those are...
I just put them as your variable. So for example, y is the response to change in your variable x. In this case, x could be an angle of your detector, whatever you're detecting the particles, and y is the amount of particles per second you're getting there.
All right, so every time you run an experiment, you're going to have a pair of x's and y's, and you can think of the y's responding to the x's. You think of it as an input-output system, and there's some uncertainty really on how y responds to x. If you had to predict what's going to happen to different x, which is not part of your experiment, then you might get a similar y to the one that you got for one that was close in your experiment, or even if you want to repeat it. So there's some uncertainty on how y responds to x, but the capital Y here on the right-hand side of this slide, what does that represent?
That represents the collection of all your data. So in that sense, is the collection of both the x's and the y's.
Oh, so what capital Y is really all the x's.
Including the errors. So in that, the error bars are also included.
Right. So when you say that these things are random variables, that's easy to understand if you think of here we have the red curve here is like very nonlinear, but you can think of it also as a linear curve if you want to make this idea simpler. So you could be trying to figure out what the slope of that line is, and that might be one of your parameters.
And we will do that in the examples after.
If that red line were just a straight line, that would be a linear model. And so the alpha would be something in that linear model that helps you figure out where the line is. And you said that alpha is going to be random, capital Y would be random. In this example, or a simpler one, a linear one, your capital Y, as you said, I think would be the collection of all the data with the uncertainties that surround how they're related. And so in that sense, the capital Y contains the data points themselves, which are not random. So when you say that everything is random, I just want to make sure that people understand that the data that we have is data, and we don't think of the data itself as random. And that's a major difference with frequentist statistics, where we think of the data as having certain properties, certain distributional properties, and it can help in frequentist statistics, which is not Bayesian, to think of the data as random because we want certain distributional properties.
Exactly.
In Bayes, we don't use this. We use different premises. And in Bayes, typically, it's not helpful to think of the data, the little x's and the little y's that we have, as being random. However, the relation between them has some randomness in it, and that's inside your capital Y. So for the folks who are wondering why we have a capital Y and then a little x and a little y, well, it's not the best choice of letter.
Well, I'm sorry.
The capital Y, because the capital Y contains the little x's, the little y's, and some other random stuff. And the little alpha, which in frequentist statistics, people think of little alpha as being a fixed parameter.
Imagine that.
And they don't really assume any distributional properties about it. And then they were surprised when they have some uncertainty about what that alpha should be. Whereas in Bayes, we think of it as being random, and we're going to find out more about that right away.
Fantastic. Thank you so much, Frederi. Very good explanation. We already dwell a bit in detail in this expression, but let's separate the terms by how usually people call them. It's the posterior, the likelihood, the prior, and the evidence. And I added some simplified description of how I see these things. So the posterior is usually what we want in this type of analysis. We're after a distribution of alpha, which we're saying is random, given the data, the collection of data that we observe.
So the capital P, let's just remind everybody what capital P is.
Please.
Capital P, we were having this discussion with some colleagues like maybe yesterday or the day before. I mean, I'm having this discussion with my nuclear physics colleagues all the time. Should we use the letter capital P or the letter little p?
Yep.
Does it matter? And this is all just notation. But here's in nuclear physics, apparently people love to use the letter capital P for continuous variables like a parameter in a linear and nonlinear model, like an alpha. And that capital P then really is representative of the density, the probability density of your variable. You can also think of it as a probability itself if alpha happens to be using discrete values only. Anyway, it's something that has to do with the probability of something happening. And I hope that everybody has a kind of a good handle on certain types of densities. Like, for example, if we know that something happens to be normal or Gaussian, you know, you have that like bell curve, that's the density. Or sometimes you have things which are like waiting times, and that can happen when you're trying to wait until you're going to have the right to press the button in your experiment. Like maybe it'll take a very long time, and then you might use an exponential distribution where the density looks like a curve like this, which has a heavier tail than Gaussian, because, you know, maybe you'll be dead by the time they let you use the, you know, the accelerator, you know. So that's a random number too. So yeah, these things were the capital P's that we see here mostly in these examples. I think you're going to show us here are densities. Probability densities of continuous variables.
We are not dealing with discrete variables here, but you're right. Indeed, the notation usually, at least in nuclear physics, is with capital P.
Yeah, whereas probabilists would use little p, but it's just notation.
But that's okay. Tomato. Tomato. So at the end, this posterior, which is what we want, is going to be a combination of the likelihood, which is what we think happened. And that's what at least when I'm thinking of the data being random, is I'm trying to find a model to explain how the data came to be. And that involves the model that I'm using, the little f, but that also involves any details, for example, in the experiment, that one of the detectors might not be working or was reporting an under value for the uncertainties, etc. The prior is the things that we know beforehand, and that we're going to try to put as much as possible without biasing our results in an incorrect direction.
Well, let me just pause here for a second. And for the moment, the gray box here in the denominator, this evidence thing, just you can forget about it. It's not really central to understanding how Bayes works. It's a normalizing factor. It's very helpful to write it in, but it's not central. Let's go back to the purple, red, and blue. I'm kind of colorblind, just making sure.
Okay. Yep, purple, red, and blue.
So the purple, red. So the prior, I would say it's not what we know; it's what we believe.
Okay,
it's what we believe.
Very good point.
It's what we believe. It's what we believe ahead of time before we realize that there's some data inside of capital Y that might help us update our beliefs. And we hear that a lot. People say, "Yeah, Bayes is great because you can update your beliefs based on the experiments that you can observe." So the observations are inside capital Y. Capital Y also contains some random model that explains why things aren't exactly according to the model. And alpha are parameters which are inside the model, and we think they're random. We believe that they're random, and we have additional beliefs about how random or how unrandom they might be. And all of those beliefs, before we even look at the experiment, these things are inside that blue box, the prior. It's what we believe. And Tio Pablo, did I mention that the Bayes is named after Thomas Bayes, who was a Presbyterian vicar?
No, you didn't.
I think it was in the 18th century.
Okay.
In southeast England, so in a very rich part of England. And he was a Presbyterian vicar. There was no such thing as mathematicians by training. I mean, you didn't have really doctorates in mathematics much at the time. I mean, people had independent wealth, and then that allowed them to think deep thoughts about various fields of knowledge, including mathematics. And so he was a very intelligent mathematician, although his regular job was to be a Presbyterian vicar, and, you know, he had his chapel and everything else in a little touristy town called Tunbridge Wells. It was a tourist town where people would come from all over Europe to drink the waters of these wells. So yeah, he had to deal with, you know, it was kind of interesting, like it was like the Beverly Hills of southeastern England in the 18th century. I think it was 18th century. Because he was also independently wealthy, that gave him, and his job was not really a full-time job. That's how he became such a great mathematician at the time. And we don't have a lot of time on this video, but I encourage you all to try to look for biographical information about this fellow, because he was extraordinary, very, very original. And that's how hundreds of years later, we're using the ideas that he thought of by himself in his corner, which he then discussed with a few friends, and they were still using these ideas today.
Thank you so much. Fantastic historical context. Okay, let's. I have a couple of examples of how this prior might look like. For example, you could say I'm going to place a Gaussian distribution or a normal distribution.
And I'm sorry, the reason why it's quite interesting that he was a Presbyterian vicar, he was a very religious man. And at the time, this is like at the beginning of the Enlightenment, the people who were atheists at the time didn't understand any mathematics or any science. They were just atheists because they didn't think that what the Catholic or what the Anglican Church was saying made any sense. So they decided, no, this does not work. Whereas the folks who were mathematicians and physicists and other scientists, they usually had very strong religious beliefs, including Bayes, including people like Blaise Pascal, all sorts of folks who we think today as the kind of the fathers. There were a few women at the time, so we think of them as the fathers of modern probability, modern other areas of mathematics, physics. They were all very, very religious people, including Thomas Bayes, whose job it was to be religious. And so does that surprise us then that the priors would be a belief about, it was like a religious belief.
I see.
And I myself am an atheist, and my belief is Bayes.
Very well, very well. That is your prior belief.
Yes. And I haven't
You haven't checked.
I have not found evidence to the contrary.
Fantastic. Exactly. That's that, and that's where I was going. Thank you for it. Yeah. Anyways, this is an example of a prior. You could also have priors saying, for example, I know that alpha, these particular parameters, is bigger than 0. And then you could truncate it or find another interesting way of doing this. But the point is that
physics, this happens a lot. People know some stuff about their parameters.
Yeah. The radius of my nucleus better be positive. I haven't observed a nucleus with negative radius.
Not in our universe.
But the point is that a lot of the effort is usually put on how can you transform all that knowledge or beliefs into mathematical formalism that you can actually put in your probabilities. Then in the likelihood, I'm going to put an example that most physicists know about because I have seen a lot of folks talking about it.
And before that, real quick,
go ahead.
So this red box, when we say it's what we think happened, the way to read this notation is really quite simple. It's the chance of whatever it is you're observing, given that the parameters might be some number alpha.
Exactly.
The chance. And why is it a chance? Because whatever you're observing inside that capital Y, there's also some random stuff. So it's never going to be exactly, it's never going to be an exact relation between the data that you have.
Exactly.
And that's why this red box also is a probability.
Yep. And that's why I usually imagine my data as random, because even if I knew the parameters, there is still a process that takes a given prediction of alpha and adds some random noise to that. I imagine it.
Yeah, I mean, mathematically it's really equivalent. So we can think of it that way as well.
Anyways, so maybe if you have been involved in any statistics in physics, you might have heard that, oh yeah, we're going to model this through e to the minus chi-square, and chi-square usually yeah. So and that confused our friend Frederi here. Chi-square, we usually define it as the difference between the observed data, these y sub i's. I don't know where my mouse is. It's there. These observed data y sub I and our model predictions. And if you think about this for a bit, it makes sense. Trying to find values of alpha where my model is perfect, basically passes through all the data. But usually that shouldn't happen. Like if your model is exactly passing through all the data points, that's probably a sign that you're overfitting. And not only that, is that this formulation, whenever we as physicists says, I'm going to write my chi-square, and I'm going to minimize chi-square, and I'm going to explore the vicinity of chi-square, you're making a lot of assumptions on how that data came to be. In particular, you're saying all of these came from a Gaussian error. I'm believing that I know the size of my errors.
If you're wondering why he said that, I'll have to explain in a minute here. Keep going.
And many of those things might be incorrect. So this is one of the most basic things you could do starting in statistics, and usually it's better to try to consult with the experts to improve it. So expert, improve it.
Well, I mean, not much to improve necessarily. This is just a very common idea. It's the case that the function f is nonlinear. This is nonlinear regression. It's just ordinary regression with a linear and nonlinear function. If your function f happens to be nonlinear, but you really are darn sure what do you think kind of function it is, it's just exactly the same as linear regression, because what you're going to assume is that the difference between f of xj alpha and yj is a random element. That's what you're going to assume in your model. That element is a standard or non-standard normal variable. While the sigma j squared in the denominator is a way to standardize your variable, so that its variance would be equal to 1.
Or we interpret it as the error of that particular variable. So, for example, this fourth point will have a very large sigma J in comparison to the others.
People report that in their research, but I'm always very skeptical about what these folks report. But it's what they report. So then we figure that we divide by the sigma j that's been reported. You square it there because the numerator is also squared in that expression in the sum of this thing called chi-squared. And when you add up a bunch of normal variables together, which all have the same, they might also have zero mean because the function f is supposed to cancel the means of whatever errors are happening, hopefully. And then you divide by sigma squared, it standardizes thing. You're starting to add together things which, if you're really lucky, really are standard normal variables, which you've then squared. The sum of the square of a certain number of standard normal variables, if they're independent, that variable is a random variable which is well understood, and its distribution is called chi-squared.
Chi-squared is the distribution.
So chi-squared is the name of the distribution, and it's extremely bad form in probability to use the same name as for the name of the variable. But that's what physicists have been doing for a long time.
For a long time. Yep.
And of course, what's the problem with that is that maybe we got the sigma j's wrong. Maybe the errors are non-Gaussian. And then all bets are off.
Maybe they are correlated.
Maybe there's some sort of bias, and then you really shouldn't be trying to do this because you're not going to be taking into the fact that there's a bias in your f, and you're minimizing the wrong thing. All this thing is fraught with difficulties, and it might be better to think a little more carefully about at least whether the difference between the yj and the f of xj alpha, at least whether that thing is normal or not. And especially another issue is that why would these things be independent of each other? Maybe there's some dependence. And if you can figure out if you can figure out from speaking with your experimentalists how the data points might be connected to each other rather than being independent, then you're also ahead of the curve in terms of not making mistakes due to correlations between your data points.
Exactly. Thank you so much for it. So in that, I'm going to transition to what a typical day of a Bayesian statistician that wants to help physicists looks like. And we are actually made already a fantastic introduction because usually those are the type of discussions that appear here. So let's go through this. And in here, by the way, this experimental friend that I have, sorry, this is a typo. This shouldn't be experimental friend. This should be base friend.
Base friend.
Yes. Oh, okay. This fellow here with the hat and the bird is representing Frederi. Because
why does he have a hat, and what's the?
Because you usually have a hat and you usually have a bird on your hat. It's just that we're outside, so the bird is inside the hat.
Oh, the birds are not. Okay. Got it.
Okay, so this is how this usually goes. When you're trying to collaborate with a statistician, they might ask you, what is the previous knowledge, for example, if we're going to put priors. And then our theory friend comes and say, well, the nuclear radius we think is around 3 Fermi. Remember that I mentioned that one of the parameters there was a nuclear radius. And then a good question will be like, when you say around, what do you mean? Between 2.5 and 3.5, it is a Gaussian, it is a skew. What is exactly happening there? And most of the time, expert people
If y'all don't know what a skew is, email me.
It's basically if your thing is tilted. So a lot of the work is trying to figure out how to quantify the information that the experts have. So I have seen you do this before. And of course, interrupt me if you have any comments on this story. And the next question might be, how was the data taken? And then if you're lucky, if you're collaborating with both theory and experimental friends, your experimental friend might tell you, well, in this case, we had 2 detectors, one precise that was less than for x less than or equal to 2, and one that was used for x bigger than 2. Actually, the second one is not that precise, and we don't trust too much the value that is around 2.3, which is a fantastic piece of information because it might be that the point at x equals 2.3, something happened in the experiment. We need to think if we should treat that point as an outlier. And we work in a project together in where we were trying to fit density functional theory to nuclear masses and radii. And by talking to the experts, we realized, okay, the radius for oxygen is not going to be well described for these procedures. So you know what? We're going to treat that independently as a separate case, and it didn't bias the entire. It's not that we excluded it, but we increased the error knowing this. So that is important to take into account. And another usual question that our statistician friends ask is, can we explain this with other models? Is this the only model that we're going to use? And some of your theory friends might say, no, of course, this is the only model that is consistent, until another theory friend comes and says, no, there's my model, or the model that these other people are doing that also explains.
And at that point, when the statistician gets to that point, honestly, that's like where the little warning signals start going
like,
off.
oh no, oh no.
and I know that it's going to take days and weeks probably to get to the bottom of the story, because they're going to have to like agree to disagree. And and then these two groups, they both have grant proposals at the DOE right now, and so they're trying to
the
find
Department of Energy.
Yeah, they're trying to find some angle where they can try to pretend like the other person's research is worthless. And but the statistician is not a fool typically, and so eventually we get to the bottom of it, and then most of the time what we decide to do is that we say, these two models are probably equally valid, and they aren't consistent with each other, so something's got to give. And in the end, since they're probably both of the teams of researchers are good, we can look at their records if we need to, or if we can just trust that they're okay. And then you can see that their results are inconsistent with each other. There's no way to get these things to match. Even if you take their reported uncertainty quantification into account, they still don't match. And so what do we do then? The only thing that you'll be able to do at the end is say, well, if we have to trust these two groups of researchers and there's no way to get the results to match, we're going to have to then use these two models in such a way that we're going to get a larger quantification of uncertainty. So that, say one of these models uses a certain approach, and the other one uses a different approach, but there's value in both of these. So let's see what happens when we decide to say both of these methodologies have some validity.
Exactly. And by the way, Frederi hasn't looked at these slides, so everything that he says is exactly what is happening in my cartoon world. So I nailed it. This is usually what happens. And this idea of combining the predictions of multiple models is called Bayesian model averaging or Bayesian model mixing. If in this case that I'm putting in here, you're going to take into account the different locations or X values in this case, in where one model has better expertise than the other, and that's the example that we're putting here. And the final part of this story is that once you have done all this, you need to say, okay, we're going to write Bayes equation, Bayes theorem, and we're going to need to sample posterior distributions. We're going to need to evaluate what the model predicts for different values of alpha. And one approach of doing that is through what are called Monte Carlo samplings, or Markov chain Monte Carlo samplings, in the case in where you have to follow a chain.
Who's this Markov person anyway? Who is this Monty? And Monty. Oh, Monty's over there. It's one of my dogs. And who's Carlo? I don't know anybody named Carlo.
Oh, technical difficulties.
Yeah, technical issues.
So I don't know about Monty, but I think Monte Carlo is a place for betting. And I hope it doesn't start to rain, because then we will be.
Chance of it starting to rain.
What is a prior belief? Anyways, there is a problem. If your model F for a given value of alpha takes a while to compute, and a while I mean a second or more, then you're in trouble, because whenever you need to do Monte Carlo samplings or Markov chain Monte Carlo samplings, you might need thousands or millions of evaluations of your model. And
so before we go there, I want to real quick. Let's go. So we're going to talk. So Pablo here has done a lot of work on trying to improve the speed and accuracy of these numerical methods. So it's really important to talk about it. Before that, I wanted to take a quick second, because this is Bandcamp, right? And one of the things that the Bayesian analysis of nuclear dynamics collaboration does is, well, the reason that NSF trusted us to do this work was because we said we were going to do proper Bayesian model mixing, not just Bayesian model averaging. And so what is the difference? Well, Bayesian model averaging is one way to mix models together by using Bayes. It's the simplest way. And this is something which appears, I think, fairly clearly in our so-called manifesto, which was published a couple of years ago. Bayesian model averaging says, we think that one of these models, maybe there's a couple that are good, or maybe they're all good, and maybe we're going to get some Bayesian evidence that they're all good, but each model is good by itself at some level, and we're going to put a prior on how good these models are. So if we don't want to start fighting with people, then we're going to assume that every one of these models at the prior level is equally valid, so they'll have equal weights at the prior level. And you just use the same ideas as Bayes, and then in the end, with all the data that you have and all the evidence, you end up with the posterior probability that each model is maybe good or bad. So this is not a general mixing procedure. This is, I think we referred to it as the M-closed framework in our manifesto. Assumption, yeah. And it says every model has its own inherent validity, and we're going to figure out what the chance is that this model, that model, that model are the best ones. And every model ends up with the posterior probability. When we're doing Bayesian model mixing, we take all the features of every single model. And there's only one way to do Bayesian model averaging, but there's a billion ways to do Bayesian model mixing. And some of these ways are not even Bayesians. These are the Bayes inside of it, and the mixing is on the outside. So there's a million things to do. What we want to try to do in the mixing arena is to try to use the features of each model that seem like they're doing a good job, combine them with the good features of some of the other models. So we're taking these models apart, putting them back together in a maybe it's an arbitrary way, but typically when you allow yourself to do model mixing rather than forcing posterior probabilities on each one of your models, you're going to end up with better prediction. And that's what we're all after, better prediction. So now let's get to the numerics.
Fantastic summary. The final thing with respect to everything that Frederi said just increases the computational complexity of what you need to do.
Okay.
So the final comment on this is that if your model takes...
We need to use the Las Vegas method, not the Monte Carlo method.
We need to use the Las Vegas method. What is it?
I just made it up.
Okay, very good. We need to use the Las Vegas method. Anyways,
the Macau method.
There is a lot of research in trying to make these computations faster, and that is called emulators, and we're going to talk about that in Bandcamp as well. So after you go through all that very hard work, you end up with what is on the screen. You end up with a distribution on your parameters. Let me say that I have parameters alpha 1 and alpha 2. So you get a posterior distribution for each one of them. You get a correlation plot between both of them, which is super important.
It looks like an accretion disk of a black hole.
Yeah.
But it's not?
Yeah, no, it's not. No, it's not. It's just the Monte Carlo sampling of millions of parameters. Maybe the computer became a black hole for that much computation power. And in here, I just made this example up, but I'm just showing what Frederi was saying in terms of validities of each models. Remember in the cartoon before that our theory friend 2 that had a flower on their head, the model they were proposing was supposedly not very good at small values of x, and that is what is shown in here. It's able to reproduce some of the data, but maybe not this one. It's not capturing that diffraction pattern, but maybe some model that can be good somewhere else. And we want to draw is expertise from the part that is able to explain well, and that is what model mixing is all about. So one of my main points that I want to make in here is that the only way to make this picture work is you need to have collaborations with everybody. You need your theory friends more than one. You need your experimental friends. You need your statistician friends, and you need your computer and your mathy friends. And that's what.
Yeah, in fact, that's right. There's some computer scientists are really good at computation. Some applied mathematicians, they're calling themselves computational mathematicians now. They also are very good. Those are not exactly the same computational field. It's good to have folks from both of these terrains. Yeah, it is.
So now we're going to transition to the Jupyter Notebook time. Let me try to... Oh, that is a closing remark. Let me get out of here. And we're at 40 minutes. I think we're fine. We're going to go through this. And I hope we're not boring people to their deaths. And then we're going to come back to the closing remarks. So having discussed all that, and I think we will be fine if we finish in the next 15 minutes in terms of rain, I'm going to show some code.
The chance of rain has been 15% all day.
All day. Yeah, we'll be very unlucky
if it rains.
Okay. So here is a Jupyter Notebook code that we're going to make available for everybody to play with, and we just basically want to show a couple of examples on how to practically do this for a simple case, and some of the things that can go wrong. So I'm not going to go fully on all the details of the code. What you can see in here is that you can specify your own data. I am starting with a true function that actually I shouldn't have show you the true functions, but now you see it. That is what is going to generate my data. But usually I don't have access to this. I just have access to a model. So how does this look like? This is the realization of what we are after. The orange curve, I don't have it. Remember, I'm just showing it.
It doesn't look anything like what you just showed us. So let's just.
It doesn't look like the curvy things.
No, the one that you just showed us now, like.
Oh, in the presentation?
No, never mind. Just keep going. Yeah, keep
going. Well, maybe that is the point. You will see in a second. But suppose that you observe some data blue, so that that is depicted in blue, and your experimental friends told you that they measured this with some error bars, and you want to fit a model. And the first thing that we think, let's just fit a linear.
Yeah, it looks totally linear. This is going to work.
This is going to work. It looks linear, right?
Yeah.
So, all of this part is defining the likelihood, which, by the way, I am assuming that I have access to these errors, that these errors were correct, and the distribution was Gaussian. That is, most of the time, not the case. But I'm going to assume that for simplicity.
Yeah, we're just doing this as an example. Yeah, I mean, a lot of times it's fine.
So we have our likelihood function. We have our prior function that we're going to put on these two parameters. My parameters are alpha 1 and alpha 2. And the meat of the code, the the serious part is whenever we have to do a metropolis algorithm. That is a specific way of doing Markov chain Monte Carlo. And the idea of the metropolis algorithm, we shouldn't explain it in detail, but basically it's exploring the parameter space. Let me go back to the presentation for 1 second.
So, Pablo, have you ever seen anything cuter than these two creatures right there?
Oh wow, we have a couple of goats. They're so cute.
They're sheep.
They're sheep. Yes, sorry.
Their names are Nori and Proudfellow.
Yeah. So what the metropolis algorithm is going to do is going to try to explore the parameter space, comparing samples and seeing how each one of these values relate to explaining the data. We can talk about that in more details in Bandcamp, and if, of course, you have questions, we're more than happy to help. But this is the algorithm, and let me show you the results. So in the first case, we're going to assume that we have known and correct errors. So everything that was handled to us is correct.
Yeah, and we know that we're over time that what we wanted to do, but let's talk about what happens when this doesn't work after you run through, because a couple things to talk about.
Yeah, fantastic. Yeah. So this part of the code is going to do the metropolis thing, and as I told you, you need to sample many thousands of times your model. And in here we're aiming for 100,000. And you see, I hit click. And this takes about, I don't know, 5 seconds, 10 seconds, maybe now less because I'm not in the battery. I'm in the battery instead of a cable. But within 10 seconds, I was able to sample 100,000 points. And once you plot that, this is how your predictions look like. So I have...
And that, the 95% band. Credibility band.
Credibility band. So we should have put it as credibility band?
It's a the Bayesians use the word credibility instead of confidence.
Okay, yeah, well, I put neither.
Yeah, just because we're the band.
We're the band, yes, exactly.
The band,
Interesting features. So you see that when compared to the true function, I mean, it is close. It's not doing a bad job compared to the red one. It actually encompasses all the points within their uncertainty levels.
What about the two that are out there?
The uncertainties overlap. These.
Oh, I see what you mean.
And in this case, we have, I don't know how many, like 10 points, 7 points. I don't remember how many I used. But you will expect that if you're plotting 95 confidence credible intervals.
Credible bands, yeah.
Yeah. 1 out of 20 points will lie out from that. And that should be fine. Like right. that you don't expect everything.
This looks about right, because that one that's like the second to the right is kind of close to getting out, but it's probably within its own 75th percentile. And so this looks about right. I would say the uncertainty quantification in this picture is pretty good.
It's pretty good. Thank you so much. And that is coming from an expert. And one important thing to notice
You're gonna get electrocuted, little boy. Sorry. Sorry about that interruption.
Yeah, that's the sheep, not the goat. One interesting thing that I want to comment from this, Don Frederi, is like, look that the error bands are not linear. I'm feeding just straight lines. How come I end up with an error band that becomes smaller in this region and then increases? You know how that happened?
No.
Well, because these error bands are done by sampling from the parameters, creating, I think, 10,000 actual predictions, and then taking the confidence interval on the predictions themselves.
The posterior predictive distribution.
There we go. So that's very important.
Yeah. So there's this thing called the posterior predictive distribution. You predict your parameters using Bayes. You end up with posteriors for your parameters, and then you plug them back into your original model with the original noise, and you assume that the original noise in the original model and the posteriors of the parameter are independent of each other. And when you do that, that's actually a mixture. And that mixture is called the posterior predictive distribution. And interesting things happen, as you just saw in this picture.
This is the posterior distribution of the parameters, alpha 1 and alpha 2. And you can see more or less around where they are. I will explain what the red lines are in a second. But interestingly enough, you see that there is a negative correlation between the two, which makes sense. If you go back to this plot and you say, I'm feeding a straight line, if I want to continue being consistent with the data, if I increase the intercept, which is alpha 1 in this case, I need to decrease the slope to be able to still be within the points. Can you see that? So my point with this is that it is important also to try to exercise intuition, because if this had come out positive, I will be very puzzled that I made a mistake in the code. I still might be puzzled that I made a mistake on the code, but at least this is telling me that things are aligning with my intuition. The red lines in here are showing the quote-unquote true values. That makes no sense because my true function is not a linear function, but what I was trying to think is what happens if what I'm interested in estimating, in predicting, is the slope and the value of the true function at 0. And the true value, the value at 0 is 0. I just define it because it's a sine function, and the slope is 1. So I'm just showing that everything worked out in this case, and we're actually recovering what we wanted to recover within our uncertainty bands at that location. And this is a very similar situation to, for those interested, the way that you extract the proton radius from electron scattering data on protons. And I work on that, so I'm very used to extrapolating to calculate the derivative at 0, and I said, let's just use that as an example. Let's look at the second case. What happens when we have one outlier, one incorrect error scale? And by that, I mean the following. We have the exact same data, but now you see in black here, this was our original point that, by the way, all these points were obtained by sampling. We have one of the sheep that escaped.
This is Lori. I'm going to pick her up in a second.
Yeah.
So people can see her.
Yes. So anyways, these points were obtained by sampling from the true function and adding the noise that corresponds to it. Is a random added noise. But basically what I'm saying in here is that the people that obtained this data point underrepresented the uncertainty. And even though the uncertainty should be this huge line, they're reporting something that is 5 times smaller. And now that skews our entire function to really pay attention to this point, even though it shouldn't. And now everything is tilted in comparison to how it should have been. And if you look at the error bands are actually smaller because I'm putting a tighter constraint on my parameters, even though it's a wrong constraint. So I'm arriving at smaller uncertainties in a wrong way, generating wrong results.
No, that is misspecification.
That is misspecific. Yeah, exactly.
Yeah, we've misspecified so it's a misspecification. Well, it's an incorrect report of the uncertainty in one experiment. Throws everything else off because we only have 7 data points here.
And how do you usually?
And that's typical in nuclear physics, right? It's typical that you're going to get only 7 data points.
It happens. Yeah. Sometimes you have a lot of data and you don't know what to do with it, but sometimes you have a small amount of data. By the way, in here you see that we miss the mark by a lot.
Totally.
And that is because we're underestimating our uncertainty.
So that's the location of planet Earth in our own.
By the way, Don Frederi, how will you solve this if this was a real problem and we suspect that we don't know exactly the size of this error or this noise? What will you do?
Oh, so if we suspect that the group who's reporting this uncertainty underreported, well, we could arbitrarily increase the uncertainty.
That's one way.
Yeah. What were you thinking?
I can add my sigma as something that I do not know. So I add a scale and I say, not only am I going to estimate the parameters of my f, of my function that I'm adding, I'm going to say that in my likelihood model, whenever I'm coming here and I write my likelihood model, let's go up. In here, this likelihood model is assuming that sigma is a known thing. It's the same thing as with the distribution we had before. But I could treat sigma as a random variable, or at least put a scale on sigma as something that I do not know, and I'm going to estimate at the same time as I'm estimating the parameters of my physical model.
Yep.
That makes sense?
Yep.
Fantastic.
You're saying we have one more parameter estimate. It might be a scale.
Yep.
Yeah.
Yep. Yeah. And
all these different sigmas could be different, but we could say
we could say
they're all part of the same scale, and there's one more parameter to estimate.
Exactly. Yeah. Sorry, a hair got in my eye. So my third case, and I have two more.
I'm sure it was from Nori. Now she's stuck.
Oh, poor Nori. Yeah. The third case is, suppose that we have new data available that we feed our model, and then a new experiment comes in very far away from where we have calibrated our model, and it looks like this. So this is our linear model that we were feeding, and we were very happy. But now
it looks like a sine function.
That looks like a sine function because originally it was a sine function, and we were just restricting ourselves to the part that it looked linear. But if now this new data point comes and we try to refeed our model, we're going to get something that is just awful. And this thing is, of course, not describing the data very well. And the reason for that is because the model that we are assuming is wrong, and we're not taking into account the model error. We need to either find a way of increasing our uncertainties or change model, which is what I'm going to propose. When you see this type of behavior, you may say, well, a linear function might not cut it, or the physics that I was using might not be enough. Let's try to develop something new. And in this case, by the way, just an example, if you were to do this in Monte Carlo sampling, the red point is not even in the picture. Like the slope parameter is around 1, and this thing is between 0 and 0.3, so it's way far away. We totally screwed this up. So my final example is, let's say that I want to use a parabola to test this thing. Now I run my Monte Carlo approaches. I end up with this uncertainty band that graphically they look interesting. In the same case as a linear model, since I'm doing the posterior predictive, this thing is just going to be not just a parabola everywhere.
Can you pause the recording for just a second?
I could, yes. Here we go.
She's panicking. Hi, Nori. Come here, baby. Are you? Oh, you're recording with the other phone, yeah. This is Nori. She wanders a lot. Not all who wander are lost. Yeah.
Okay, so we're almost done with examples. We see this prediction. The uncertainty band is actually encompassing the sine function. It doesn't have to, because again, we're using a model that is not the correct model, but is doing a much better work than the straight line. And this is the posterior distribution of the parameters. Now we have a third parameter, which is the term that controls the x square. And by the way, when I was doing this in your house, that you heard that I said, "Oh, finally, I solved it." The problem was that I was using the same Monte Carlo steps for the third term, and the third term, the scale is much smaller. So that is one of the details that you need to pay attention to whenever you're doing these type of things. It's not trivial to set up what is a good scale for the Monte Carlo sampling. Very well. Those were the examples of the code. We are going to distribute that so that everybody can play with. Let me go back to here, and we're going to close. Oh, and by the way, we have this fantastic quote that says, "If Bayesian statistics is the love story between data and probability, then computer science is the roses and chocolates." Do you know who said that?
Tio Pablo.
Yeah, me. I was joking with Cal about silly things to say about all this, and this is what I came up with. Anyways, these are the closing remarks. We hope that you have had a good time learning about these Bayesian ideas and methods with us. Here at the Bank Collaboration, we are trying to make a set of software. We're not trying, we're making a set of softwares to help on all those things that are needed along the path. And in doing the Bandcamp on Monday, May 22, we're going to talk about many of the tools that we have been able to develop, including emulators, model mixing, and a part that has to do with experimental design. We didn't talk about that much. Sorry, go ahead.
No, nothing.
Okay. And this is basically the schedule for what we're going to talk about. And before we close for real, I want to add this challenging problem to the folks watching us home. Do try this at home, which is, could you be able to make the same analysis that we did, but do not use the given sigmas, but rather try to estimate a size of sigma. Basically, add a sigma as a parameter in your likelihood that will tell you the size of the noise across all these samples. And that, I think, is a good exercise to put us in the path of not assuming that every time that you get error bars from an experimental program or whatever else you're getting the data, that all these sources of uncertainties might not have been necessarily taken into account. And that is all that I have to say. Do you want to say any other closing remarks?
Well, so that's a good challenging problem, because in fact it's very realistic. You might have a whole entire group of folks who are working with various experimental instruments, kind of in the same direction. They're trying to do the same, estimate the same physical quantities, and even if they're working with different instruments. There's a culture in this whole group of folks, with the various different locations where, they don't want to be, they don't want to look like their uncertainty levels are 50 times larger than the rest of the folks. And so it makes sense actually to say, well, there's a cultural norm in this field where they're all underreporting uncertainty. We think the uncertainty is too small. Everybody in this group are underreporting uncertainty, and this is very frequent actually in all sorts of different areas of application, where people always underreport uncertainty, especially when they don't use Bayes. But it makes sense to have an additional parameter to say, we think the uncertainty has been systematically underreported,
And we're going to try to estimate
and that's
that.
what, and this particular challenge here helps you get around that problem.
Very well. Thank you so much, Don Freddy. And thank you to all the sheep. And thank you for watching. We'll see you very soon. Bye.
Hold on. So for those who want to keep watching, there was a couple other details that I wanted to talk about regarding priors. Are you still recording?
Yeah, I'm still recording.
Okay, so for those who want to keep listening to the end of this video, so there are issues that can occur with setting priors, and as you know, we talked about the issue that when you're trying to fit two sets of data, one is the experimental data that gives you the response. You got your x's and the y's, and they might be related to each other. There might be a nonlinear function between them, and then you might assume that there's additive errors. In other words, the f of x minus the y. We're going to model it as a certain type of statistical error. People use Gaussian errors. It's very common. That means she's hungry, but she's all right. But when you're in a data limited situation, it's philosophically there's a reason to believe that the errors that you're looking at are not Gaussian. It has to do with degrees of freedom, and so you probably heard of the notion of t-distribution, and those things are what you obtain when you have uncertainty on certain things like the scale of your phenomena that we were just talking about. And if the number of data points that you have to help you figure out what your scales are is limited, then these so-called t-distributions are going to have what we call small degrees of freedom. And when that happens, the tails of those distributions end up much heavier than Gaussian tails. And when you start drawing pictures of how far away you need to be in the 95th quantile, credible interval, or whatever, it goes much further out than you would with the Gaussian model. And so in a data limited situation, which happens frequently in nuclear physics, it's probably a good idea to investigate whether using t-distributions for your error terms is maybe a better idea than Gaussian distributions. And even you can do an intermediate thing, like you can have an exponential distribution instead of Gaussian, much shorter, much lighter than t-distributions with low degrees of freedom, but still heavier than Gaussian. So these are all things to explore. We were talking before about when you do your uncertainty quantification, and if you had, let's say, 20 data points, you expect one of your data points to lie outside of your posterior prediction at the 95% credibility level. Remember that? You have 100 data points, you expect 5 points to lie outside of your posterior predictive credibility intervals or regions. 5 out of 100. That's 95. That's like 5%. And if those are off, like if you do have 100 data points and those numbers are off, because with 100 data points you have 10 instead of 5, you're off. 10 outside, what does that mean? That means that your intervals or your regions are too small. That means your uncertainty is underreported, and that means you're lying to the public about how sure you are, and nobody wants to be in that position because, look, people, and I don't want to point any fingers, but there's other areas of science where people have been doing this routinely, and now the public does not trust these scientists anymore. Lucky for us in nuclear physics, the public doesn't know a whole lot about it, so it's all right. There's other areas of science where people know a lot, and they don't believe the scientists anymore because they've been underreporting uncertainty for far too long and saying dumb things. So that's why these t-distributions can be very helpful. You don't want to be dishonest about your uncertainty. It is a really good practice to actually test when you're using your posterior distributions to try to reproduce the data points that you already had to see how many lie inside your predictive credible intervals. And if you're far off, if there's way too many lying outside, those intervals are too small, you might be needing to use those heavier t-distributions for your errors at the very beginning, at the prior level.
Exactly.
Does that make sense, everybody?
Yeah, I think. I don't hear any complaints.
Oh, okay. All right. So there's no questions.
There's no. Very good. Very good. We maybe should mention this during the Bandcamp and in talks in general. I after the project that we're doing with the t-distributions, I'm really have come to like them.
Yeah, and people use t-distributions. They don't know why, but they do, and that's the reason.
Yeah. Very well. Thank you so much, Don Frederi.
And so now I think we're going to try to also record like a 10-minute version of this whole thing, because this was like an hour.
Yeah, this was literally an hour.
Yeah.